Okay. Should be recording. Ethan, do you want to verify that it's recording for a little bit? Yeah, going down. All right, you ready? All right, we're going to be talking about exploring kernel rootkit exploitation. We have a very cool presentation for you guys today. So, we have some objectives we need to get out of the way initially, right? So, what we're going to be doing is we're going to be making a rootkit. And we want to see just how much damage a rootkit can actually do to a computer. We have 4 very interesting attacks that we'll get into in depth. For now, let's have a little teaser for what they are. Number 1, we want to perform privilege escalation attacks. This is very fancy, very cool. And basically, we're going to give root access to regular users. It's going to be fun. A lot of mayhem and carnage. Number 2, our second coolest attack is we want to successfully hide our rootkit. This is very important because we want our rootkit to be stealthy. We're not building trash code here, all right? We're building industry-grade malware. So that's what we're doing. Number 3, we want to hijack RNG modules. This is very important because, people typically think that cryptography is secure. But cryptography is not secure when your RNG modules are hacked. So that's what we're going to be doing. And number 4, we're going to be hiding files and directories from user space. And this is very important as well because, hey man, what if you have a specific file on your computer that you think is a little bit embarrassing? Well, you can now hide it with our state-of-the-art malware. And so now before we actually begin, right, I want to show you guys the topology of our attack. And then we'll get into the first attack and we'll go on from there. So, this was our original topology, right? We have the kernel space over to the right in this diagram over here. You see the kernel has a set of different modules, right? And one of the modules that we have is a rootkit. So we assume that an attacker already got in and planted a rootkit module in the kernel that we can use later on. And now we have a malicious program that's running in user space, right? So maybe a user double clicks on, a tainted PDF or something. And this malicious program communicates via IOCTL to the rootkit. And this way you can actually have inter-process communication. You can, run different commands and stuff. And you're basically you have a backdoor into the root, into the kernel, right? And this is the attack topology. And now we're going to go to attack number 1. Take it away, Nick.
Okay, so we're going to be talking about privilege escalation today. So one of the key ideas of privilege escalation, why do you want it, right? If you're hacking something, you want to have root access, you want to be able to run sudo commands, you want to be able to have escalated privileges. So the idea here is we're actually going to modify some values in the struct that stores the credentials or the privilege. So you can see here that we have these different values here, such as group ID, user ID, and we're going to modify those values to make them correspond to root privilege. So one of the problems with this concept here is that if when we do that, we're actually only modifying the credentials of that current process, and we actually want to have our own shell that's a privileged shell that we could run our commands and various hacks. So the way we're going to do that is we're actually going to bake some malicious code into the shell itself. So this way we'll have a shell that has privilege roots, basically. So then this is our new attack topology here. So you can see here that we have our modified bash shell, and it's communicating with the kernel space over IOTCL. And basically, this allows us to run our privilege commands in this hacked bash, so to speak, and gives us privilege access to the computer. And then lastly, this is just an overview of how this works. We're going to call the prepare creds function, and that's basically going to make this new set of credentials that correspond to the current process. And then we're going to actually call commit creds. We're first going to change them to the ones that correspond to a privileged user, and then finally we're going to call commit creds to push those changes to the system. And then our next hack is hiding the rootkit. So it's very important to have a rootkit hidden because if someone actually realizes this or comes across this, that our cover is going to be blown. And the way we solve that is by hiding the kernel module. And the way we do that is we're first going to figure out where the OS keeps track of these modules, and then we're going to hide that particular module from that list. So this is what the pictures here kind of allude to. So the way the OS keeps track of kernel modules is it has this module struct with the various parameters, and it's actually just stored in the linked list. And all we have to do is just find our particular module that we want to hide and just remove it from the linked list. So the way we do that is we have this hiding function here, and that allows us to just give it a node and just remove that node from the list, and that's how we accomplish hiding our kernel module.
All right. Now we're going to be talking a little bit about ftrace and what is kernel hooking. This is important for the next hack, so let's get right on into it. So first of all, what's ftrace, right? Ftrace is a tool you can use for function hooking, all right? Now you might be thinking, all right, what's function hooking, right? Well, originally it's a tool used by programmers to debug, right? If you use function hooking, you can hook into a specific function, which means you basically call that function, but within the wrapper of your own hook. So what you can do is you can call a function, let's say the function is called hello, and you call it, and you can start debugging it, right? You can see what every step is, because you can actually peer into that function, change some stuff, maybe get the return value and change that a little bit, right? So it's actually a very powerful tool. But here's the problem, right? It's too powerful of a tool. And that's bad for regular people, because now we can implement it in our malware, right? What we can do is we can actually use ftrace and function hooking to basically plant our own malicious code and run it instead of normal code. Let's say that we have a function that is used to calculate some very important cryptographic algorithm, right? Well, if we use our ftrace utility to basically hook into that and change the numbers up a little bit, well, now we can implant our own numbers, and the cryptographic algorithm is now obsolete, because it's now our own numbers that are being used. And so here's an example of that happening, right? So first of all, what we have to do is we have to identify the program that we want to attack, the address of the kernel function that we're hooking. And then we set up a struct that contains a pointer to that function. And then we go ahead and actually compute, we do the hooking process, and we enable it with register ftrace function. And at that point, we're already done. So we already hooked on, and when the hooked function gets called in this instance, right? It is actually called, but our malicious code runs instead of the intended code, right? So to the regular user, it looks as if they're actually calling that function, but in reality, they're calling our own function that's malicious, that kind of overrode it, which is pretty cool. And we can actually use this in our next attack, which is very fancy, and it's called hijacking RNG, the random number generator. So, first of all, right, security exists on all levels of computing. We have high-level web apps and stuff, and we have traffic sniffing, but we also have low-level architecture. And this is where we're focusing on for today. We're focusing more on the low-level stuff. And now, on the lowest level, especially for cryptography, there exists a ground truth of sorts that says that, all right, well, my computer is safe, right? If I create an RSA key, if I use my computer to create random numbers to use for AES or DSA or some kind of encryption, it should be fine, because how can you mess up a random number generator? But that's not necessarily the case, right? We can use malware to actually jank up the numbers for the RNG. So the ultimate question here is, how much unseen damage can our rootkit do to the random number generator? Well, let's explore that. So cryptography is based on random numbers, and there are a few areas in Linux that create random numbers. So most notably dev random and dev urandom, and this is in the file system. And this is how the Linux operating system generates random numbers normally. So when you do like math.random in Java, ultimately it'll go down to here. But the thing is, we could override the RNG generators, and then what we can do is we can basically, delete encryption that way. So over here to the right, this is a snippet of code showing you random read, and you have random read down here. And these are, again, the two functions that create random numbers for our computer. In our hack, we're actually going to be attacking uRandomRead, and we'll see that in a second. So this is just a flow diagram that explains the topology of the attack, right? So how are we actually hijacking RNG? What we're doing is we're having a user call the normal random function. Because remember, the point of ftrace, the point of function hooking, is that a user calls a function thinking that it's normal, but instead it calls a malicious program. So again, a user calls the random function. Seems totally fine, but instead the malicious random function is called. Now we go down over here to the third element here. So the result from the random function is stored in a buffer. And you might be thinking, okay, what's going on? I thought we were going to intercept the random function. Well, in reality, in Linux machines, right, we have this thing called entropy. And entropy decreases every single time you call the random function. So if we were to completely bypass the random function, our malware would actually be detectable because the entropy in the system wouldn't be decreasing. So it's actually important that we legit call the random function and we legitimately get the values from there. It's just that after we get the values, we can change it up. So the results that we got from the random function are real, right? So let's say in our buffer, we have the numbers 30, 278, and 93. Now we create another buffer called kernel buffer. We abbreviate it with kbuff. And we move the values from the buffer to kbuff. We change it up a little bit, so we make kbuff 000, for instance, and then we put that back into the normal buffer. And the reason why we're doing all this is because when it's in kbuff, it's away from the user, you can't really see what's going on, and we can control it completely. So we can have this kbuff, we change it to whatever we want, we do 000, we put it back in buff, and now we return 000 back to the user. So now a user is awaiting 3 random numbers and instead gets 000, which is crazy. So we've just completely hijacked RNG. Now the advantage is that this method is not really detectable, it's easier, and in general it's pretty cool, right? Over here we have an actual demonstration of the attack as it's happening live, right? So to the right, you can see the hook function. It's called hook uRandomRead, and this is the code that we have. Again, it's just a normal hooking function, just like the code we showed before. Over here to the left, we have a DD call to the random function, the actual random function. So this is before the attack is run. DD just prints out the bytes. And you can see over here, we have a bunch of random bytes. We have 9C99, 6854, etc., etc. And this looks pretty normal until we run the giproot uran command, right? So giproot, again, is the name of our rootkit. Uran is a particular argument that we have that says, okay, hijack the uran command, or the function. Now we run dd again, we call the same random function, and instead we get deterministic outputs. We get 20, 20, 20, 20, 20, 20, right? So this is pretty cool. We just hijacked RNG. Simple as that. And now, we go to Durance.
And now, for our last attack, we need to first explain what a Durant is. And so, this is important. Sorry. So now we explain the Linux virtual file system. Because to the user, all the different physical files, and also like little virtual file systems like sysfs and profs, those look like they're all part of one big giant file system to the user. But to the kernel, they're all separate and they all need to be separately identified. And so each physical file system is going to be identified by its own physical ID, which is going to be called usually a device ID. And within each physical device, we're going to have unique files that are going to be identified by their inode number, as well as directly identified by an inode number. And then within each directory, we're going to have what are called a bunch of directory entries, or durants. And those are going to contain a string containing the name of the durant and the file or the inode number that corresponds to that durant. So that way you can uniquely identify a directory entry or an entry inside of a directory by a combination of the physical device ID, the inode number of the parent directory, and the actual name of the file itself. Because if you have, say, a hard link, you might have the same file in several different directories with different names. And if we just want to hide one of these, we actually need this, not just the inode. And so let's actually get on to the attack now. So when files are read or listed from the directory, in most programming languages you're going to use, it's going to use the system called getDense, which is part of libc. Now what getDense does is it passes the open directory as a file descriptor with the current offsets, the number of the next endurance to read, and a buffer to write them into. These are going to pass to the kernel and is expected to write as many of the next counts durants as exist in the user space buffer before returning. Now to keep track of what files you want to hide, we can identify by the method that we just mentioned. We use length of name, the name, the ID of the parent directory, and the device ID. And these entries are going to get stored in memory within our rootkit as part of a resizable hash table because that makes it really convenient for us. It looks like that. The entry identifier. Now, to hide files and directories, all we have to do is just let that original syscall run using the same ftrace method we used last time. And then we parse and edit the original output, once again, just like last time. And so, if an entry we don't want is found at the start of the buffer, we move the rest of the bytes in the buffer down onto it and decrement the output size. And if an entry we don't want is found later on, we alter the rect length of the preceding entry to skip to the next entry in the buffer or its end. And that's it for all four of those methods. Now we're going to talk about future work, or what we can do to improve this. The first idea that we had was making hidden files visible only to our user space program. This would actually be really trivial. All we need to do is just modify the previous bit of code and give our program or shell like a really uncommon name, a weird one, and add a whitelist for it. So just like check, hey, if it's in the blacklist, but the process is in the whitelist, show it anyway. And that's really easy. The next one, which is maybe a little harder, would be figuring out how to replace our current method with live patching instead of ftrace. This is a really good idea because our current method actually requires the use of an extra piece of kernel code called kprobes. And the reason why we need kprobes is because ever since like kernel version 5.8, 5.9 or something, a really important function called kallsims or kgetAllSims, which is used to look up arbitrary kernel function names, is actually hidden from module space. So kernel modules can't access it normally. And we're using kprobes to actually yoink this function back towards us so we can actually use it again. But the issue is most kernels and most OSs aren't actually going to have kprobes enabled. Although high availability systems will have ftrace enabled because they are necessary for live patching. And if you have a high availability system that you don't want ever going down, you need live patching. And the last improvement would be container escaping, because even if you're root, you have every possible privilege you can get inside of a container, you can't really do jack outside of it. You're just kind of stuck there. But we don't really know how to do that yet. And now we're just done with the conclusion.
So, in conclusion, this research project highlights the importance of robust security measures to mitigate the risk of these kernel-level hacks. We examined various techniques for exploiting kernel-level vulnerabilities in Linux, including RNG hacking, function hooking with ftrace, hiding kernel modules from user space, and hiding directories by manipulating the RD reclin field. This research explores how these techniques can be used to gain unauthorized access, manipulate system resources, and evade detection. Thank you very much for your time, and I hope you enjoyed this presentation.